Thế là ai đi gọi đây. So today lesson is electromagnetic induction. At the end of this session, the student should be able to describe the principle of electromagnetic induction, describe and apply the Fleming right-hand rule for the generator, say and describe the Lenz's law, calculate the EMF used in the conductor for a number of conditions, and list applications of electromagnetic induction. So this is for the this is coil here. When the magnet move into this coil, it produces a voltage and current. So the current will indicate this direction. So the moving this direction, current indicate. When the moving out this direction, current is the reverse. So this is for the electromagnetic induction. So the crossing this right hand rule, the first finger direction is indicated by the flux, and middle finger indicate the current, and the thumb indicate the motion. So this is for the generator. So this is for the north pole and south pole. The magnetic flux are coming from the north pole and south pole. So these coils are moving to here, and then there will be there's the direction, the flux direction, first finger, and that direction motion, and middle finger direction is the current direction. So the current is flow away from you. So this means that there's a flux direction here, first finger, middle finger is current, and there's a that direction motion. So that this one go to this direction. In this case, the current coming to you. So this way, we have to complete the two diagrams. So this is the coil. The coil is moving. This is for the north pole and south pole. The magnetic flux are flowing. This is the coil. So this is coil side A and B. So the A and B here, so they rotate. So this is the rotation. So when this is rotating in this direction, so that this rotate, in this case, this current is coming to you and current flowing, going away from you. So this is the current flow direction in this coil. And then this direction, there will be no current, and this direction. So now current coming to you, here current going away from you. So the current flow direction in the A to B is here. The generator voltage depends on the strength of the magnetic field, plus the B Tesla. The length of the conductors in the magnetic field and the length, the velocity of conductor in magnetic fields are velocity V. So those are things are dependent. So the E equal to BRB. B is the flux density, A is the length, the B is the velocity. So we have to calculate. Find the EMF generated by a 250 millimeter length of the copper wire passing through a magnetic field with the flux density of the 115 Tesla at the velocity of 20 meters per second. So what we do, we know is that we know about the length at 0.25 meter, flux density B is at 115 Tesla, and the velocity V at 20 meters per second. What do we want to know? So that we have to calculate that E equal to BRB. E equal to 115 multiplied 0.25 multiplied 20. And so this is the 7.4. The next one is the find the velocity of the 200 millimeter length of the copper wire passing through a magnetic field with the flux density of 250 millitesla, we produce the EMF of the 1.5. What do we know? We know about the length at 0.2 meter, flux density B is at 0.25 Tesla, voltage E is at 1.5. What do we want to know? So V is, we have to calculate the velocity. So that we write the equation equal to BRB, so that V equal to E divided by BR. So this is 1.5 divided by 0.25 multiplied by 0.2, so you got a 30 meter per second. The next one is the Pauli law stated that the value of the EMF induced in a circuit depends on the number of conductors in a circuit and the rate of change of the magnetic flux linking the conductor. So Pauli law stated the value of the EMF induced in the circuit depends on the number of conductors in the circuit and the rate of change of magnetic flux linking the conductors. So that E equal to the N multiplied del phi by del D. So N is the number of time, del phi the rate of change of flux, del D the rate of change of time. So this is the one number of conductors is an N, and del phi by del D is the change of the magnetic flux linking conductors. The next one is the phi the EMF generated in the coil of the previous task. Is the magnetic field surrounding it draws from the 0.3 to the 0.1 wavers in the 1/10 of the second. What do we know? We know about the N is to 15 turn, thereby the 0.3 minus 0.1, you got the 0.2 waver, that is a 0.1 second. What do we want to know? So we know about the E equal to N d phi by dt, so the d by dt is the 2 waver per second. E equal to 15 multiplied by 2, you got a 30 volt. The next problem, find the number of turns required in the coil which can produce an EMF of 60 volts when a magnetic field of the 400 millitesla draws to the 0 in 5 milliseconds. What do we know? So we know about the E equal to 60 volt, therefore equal to the 0.4 minus 0, so waver, so 0.4 waver, that is a 0.005 second. What do we want to know is, so we know about the N equal to del phi by dt, so N equal to E into del d by del phi, so it's 60 by 80, so you got del phi by dt 80 waver per second. N equal to 3 by 4 times. Calculate the EMF induced in each coil on the transformer that has a 600 turns on the primary and a 50 turns on the secondary. If the flux of the 0.25 waver is reduced to 0 in 5 milliseconds. So what do we know is that we know about the this is a transformer here. So this was a primary and secondary coil. In this case, the primary is 600 turns, secondary is 50 turns. So MB is 600 and S is 50. So in this case, the flux change is a del phi equal to 0.25 minus 0, so 0.25 waver. So that is a 5 milliseconds, 0.05 second. So what do we want to know is that we want to know that E equal to N del phi by dt. So you got del phi by dt 50 waver a second. So the MB got 600 multiplied by 50, you got a 30 kilovolt. When the NS is 50 turns, so 50 multiplied by 50, you got a 2.5 kilovolt. Law stated that the direction of the induced EMF is always such that the resulting current wave flow will produce a magnetic field which tends to oppose the original motion, causing the induced EMF. Law states the direction of the induced EMF is always such that the resulting current flow will produce a magnetic field which tends to oppose the original motion, causing the induced EMF. So this is what is quite here. That's quite the currents are rolling. And so this will produce a north pole and south pole here, and the then magnetic flux will be produced. So when the currents are opposite, so that will be north pole and south pole like this. So this is the magnetic flux around the magnetic field. Magnetic coil, this is the around the field. So this is the right hand rule is here. So first finger directions is a flux direction. So the middle finger is a motion, and then middle finger is a current, and thumb is a motion. So this is a right hand rule for generator. So generator is a flux in the flux when the coils are move across into the thumb direction. The induced current is a middle finger indicate the induced current. The hand rule for the motor. In this case, the motor, there are two things have to be rotated. So provided so the current flow in the coil in the magnetic flux is a first finger direction. First finger direction is a magnetic flux direction. Current is the direction is indicated by the middle finger. In this case, the motor will rotate across the its thumb direction. So this is the right hand rule for the generators, left hand rule for the motors. Then you have to do the practical exercise. The next one, inductors and inductance. Inductors and inductance. calculate.
Answer what valley. Maybe those alone it. You on 12 years.
You are Java hero game.
The Kaviakis are one of the follow on and things like that.
Interdas and intertext. Interdas and intertext. At the end of this session, the student should be able to describe the cell induction and inductance, describe the construction, and draw the Austrian standard symbol for the inductors, calculate the inductance of the coil for a number of different characteristics, identify the common types of the inductors and list their applications, describe the construction and the use of the bifilars or wirings, and describe the testing procedures for the inductors. The value of the input EMS depends on the strength of the magnetic field V, the length of the conductors or the number of turns N of the coils in the magnetic field M, the speed of the conductor V in the magnetic field. So E can be calculated BLV. In this case, B is the magnetic field strength, A is the length of the conductor, B is the velocity. For the law of the induction state test, the input EMS is proportional to the rate of change of the linkage between the conductors and the magnetic flux. So rate of change of the flux is a del phi by del t. Multiply with number of times, then you can calculate the input EMS E. Where to calculate? Determine the flux density of the magnetic field. If we conductor 25 millimeter long cuts through the flux at the right angle, with velocity of the 15 meters per second to produce the body of the system. What do we know? We know about this length is a 0.025 meter, velocity is a 15 meters per second, E is a system. What do we want to know is flux density V. So the E equal to VLV. So E V equal to E divided by VL. 6 by 15 to 0.025, you got a 16 Tesla. The next problem. A coil of 150 tons is linked by the flux of the 300 milliweber. If the flux is reduced to the 100 milliweber in the 100 milliseconds, determine the voltage induced in the coil. What do we know? So that this is the number of time 150 tons, so that therefore equal to 0.3 minus 0.1, you got a 0.2 weber, that is a 0.1 second. What do we want to know is E equal to N therefore dt, therefore dt is 2 weber a second. So E equal to 150 multiplied by 2, you got a 300 volt. So this is the coil, is a current flow into this coil. So then the magnetic fields are produced. So the expanding field into the EMF, then opposite apply voltage and hence slow the current increase. So because of the into EMFs are direction, this is a small arrow. These small arrows are produced the original current flow. Original current flow is checked out by this one. Slow by the opposite field. So we have to calculate. A coil of 1000 tons carries a current which establishes a flux of a 0.01 weber. If it takes a 0.05 seconds for the current to reach its steady state value, determine the cell into volt EMF of the coil. What do we know? We know about the N equal to 1000 tons, therefore equal to 0 minus 0.01 weber to the minus 0.01 weber, that is a 0.05 seconds. What do we want to know is N equal to E equal to delta pi 30. So at the pi 30 is a 0.2 weber a second. So the 1000 minus 0.2, you got a 200 volt. The induced EMF which opposes the chain is called the EMF of the cell induction. The polarity of this cell induced EMF is always opposite to the applied voltage, so it is often called the back EMF. The property of coil that opposes the chain in the current is called the inductance error or the cell inductance error of the coil. The unit of the inductance is a Henry H. Inductance is dependent on the number of turns in the coil and the rate of change of the flux with respect to the change in the current, equal to N del phi by del I. So that the rate of change of the flux is dependent on the area of flux path K, the number of turns in the coil N, and the permeability of the core mu. The length of plus is also there. So we can calculate del phi by del t equal to mu a n by n. In this case, our del phi by del t is way of change the plus. Mu is our permeability, A is the area of flow, N is the number of time, and the A is the length of the point. So then we can calculate A equal to N into del phi by del I. It can happen A equal to mu A N squared divided by L. In this case, A is the inductance, mu is the permeability, A is the area, A is the number of time square, A is the length of the point. We have to calculate. Calculate the inductance of the coil on the 200 tons. Roll on the wooden cylinder of 200 millimeter long and having a cross-section area of 700 millimeter square. What do we know is that we know that N is 200 tons, air core is mu equal to 4 by 10 power minus 7. There is a 200 millimeter and area is 700 millimeter square. What do we want to know is A equal to mu A N squared divided by N, so that you calculate 4 by 10 power minus 7 multiplied 700 into 10 power minus 6 multiplied 200 square divided by 200 into 10 power minus 3. You got there 176 microhenry. So that we also have to calculate, in this case, metal cylinder got the metal cylinder. In this case, the metal cylinders we have to calculate. So number of time 200 time, metal core is mu equal to 33 into 10 power minus 4. A is at 200 millimeter and area is 700 millimeter square. We write the equation A equal to mu A N squared by L. So 33 into 10 power minus 4 multiplied 700 into 10 power minus 6 multiplied 200 squared divided by 200 into 10 power minus 3. You got a 462 millihenry. The symbol for the fixed air core and the variable air core, and also iron core and Faraday core. So this is a fixed air core, fixed iron core, fixed Faraday core. Here is a variable air core, variable iron core, and variable Faraday core. So this is what the mutual inductance can be calculated. So that at the end of the discussion, the student should be able to describe what is meant by the term mutual inductance, list a practical application of mutual inductance, define and calculate the time constant for RL circuits, calculate the instantaneous values of the voltage and the current in the RL circuit. When you calculate the coil of the 1,500 turns, carry the current with established in front of the 0.01 waver. If it takes a 0.05 seconds for the current to reach its steady state value, determine the set into E and F of the coil. What do we know is, we know that a number of time 1,500 turns, and also therefore equal to the 0.01 waver, and also the delta is 0.05 seconds. What do we want to know? E equal to N delta by delta. So the N is 1,500 multiplied by 0.01 divided by 0.05, you got the 300 volt. So this is that there is a chain magnetic field. When the chain magnetic field here, it induces the voltage, and the voltage can be measured at the cross and this terminal. If there is a changing magnetic field around the one coil, then the second coil will have a voltage induced by a by mutual inductance. So in this case of mutual inductance, so this is the RL circuit. So in this case, the A is an inductor, I is a resistor. When the current change the changing magnetic field, induce an EMF in the coil. That opposes the chain and hence the slow the current change. So the current IA flowing and this IV is the opposite. So the time constant can be calculated T equal to L by R. And charge circuit, when the electrical current flow here, the V T equal to Vs into E power minus T by tau. In this case, this T is L by R. So T2, T3, T4, T5, T. Then when the charging current here, so this current will be going down like this. So this is the charge circuit, discharge circuit. And charge circuit is this is a discharge circuit. In that case, charge circuit is a current can be calculated I maximum into E power 1 minus E power minus T by tau. So T tau is L by R, I maximum is Vs by R. So current flow to this coil like this. So this is I maximum T2, T3, 45 T. Then in this case, the current will be produced according to this rise of this graph. And IS circuit is IF flow into the disk coil. So A into R here. The correlations are free indicates the induce the EMF in the coil. That assists the applied voltage and hence slow the current of decay. So in this case, current are when because of the disk free, the current will be going slowing down. In this case, the T equal to L by R can be calculated. Discharge circuit is a current flow to R here. V equal to Vs to E bar by that D by tau. So tau is L by R. So in this case, current will be going down like this. So this is the discharge circuit. IT equal to I maximum E power minus D by tau. So D tau is L by R. I maximum minus Vs by R. So in this case, current will be going down like this. The inductor voltage always start at the maximum for the charge or discharge. Voltage always for I maximum Vs by R. For the charge, current will rise to charge up. And for the discharge, current will fall to discharge down. So this is for the time constant class for the RC. T equal to RCL, L equal to T equal to L by R class. So this is what you the time constant class. So in this case, this circuit here. So in this case, inductor is at 4 Henry, resistor 2 ohm, and supply voltage 0.24, and then to switch. At T equal to 0, switch is open to close. At T equal to 0, current begins to flow. The opposition to the current flow is a maximum. So at T equal to 0 is the ID is 0, VA is a 0.2 volt, and the VI is 0. And this is a series LR circuit. So I equal to I R equal to ID equal to 0. So tau equal to L by R. So 4 by 2 equal to 2 seconds. After the 5T, 5 multiplied to the 10 seconds, the magnetic field is established and the current has achieved a steady state. Therefore, the VA equal to 0 and the VRVS equal to 0.2 volt. The maximum current will flow in the circuit after T equal to 5T is IA equal to ID equal to IR. This is equal to V by R, so 0.2 by 2 equal to 0.1 ampere or 100 milliampere. So this is the on and off here. This supply and then 0.8 Henry, resistance is 47 ohm, supply voltage 25 volt. The above circuit, we have to calculate the circuit time constant. The circuit steady state current, the circuit current one time constant after switch on, and the circuit current one time constant after switch on. Those we have to calculate. So firstly, we have to calculate T equal to L by R, so 0.8 divided by 47. You got the 17 milliseconds. And the steady state is achieved after the 5 time constant. So the I maximize II equal to V by R, so equal to 25 by 47, you got the 531 milliampere. And when the switch moves from the off to the on, T equal to 0, and the university time constant is T equal to T. So then we have to see that the time constant car. So it can see well now. At the T, it reached the 3 by 2%. Therefore, the C by 2% multiplied by 531. So you got the 335 by 7 milliampere. And the switch move from the on to off after the steady state achieved. In this case, the current will flow here. And the university time constant is T equal to T. So that will be there. And this one is the 98%. So therefore, the 98 multiplied by 531, you got the 195.3 milliampere. So this circuit diagram, in the die 5 Henry resistor 10 kilo ohm, supply voltage 10 volt. The switch will be closed at the tie equal to 0. So the calculate the current flow in the inductor 1 millisecond after the initial application of power. Then we calculate T equal to L by R, so 5 divided by 10K, you got the 500 microsecond. Then from the university time constant curve, T equal to 1 millisecond equal to 2T. Then the 2T here, this will go down the 86.5%. And therefore, the 86.5% multiply I maximum. So I maximum calculated. And in this case, the I maximum flow T equal to 5T after the switch closed. So the T equal to 5T, so 5 into 500 microseconds, so 200 milliseconds. IRS maximum II equal to VS by R. So the 10 by 10K, 1 milliampere. So then 1 milliampere multiplied with 86.5%, you got the 85 microampere. We also have to calculate the currents are flowing in the inductor. 0.9 millisecond and 6 milliseconds after the initial application of the power. So supply voltage at 40 volt. The switch is closed at the time 0. Inductor is 1 by 2 Henry, the resistor 1 kilo ohm. So T equal to L by R can calculate the 1 by 2 divided by 1K, you got the 1 by 2 millisecond. I maximize equal to IR equal to the VS by R, so the 40 by 1K, so 40 milliampere. University time constant cost, you can calculate T equal to 0.9 millisecond, so the 0.75 Tesla. T and the average sway growth. So this is the average sway growth, and that will be there's a 0.75 DA. So you got the 52.8%. And therefore the 52.8% multiplied with 40 milliampere, you got the 21.1 milliampere. Equal to T equal to the 5 millisecond 5T average sway growth. So then we can calculate the average 5T, so you can see the sway growth. So in this case, our 5D sway growth, you can see it can reach about 99 points, 93%. So 93% multiplied 40 milliampere, you got the 39.72 milliampere. Then you have to do the exercise. Then DC generators are generator power. The DC generator power. At the end of this session, the student should be able to state the basic operating principle of a DC generator, apply the Fleming's right-hand rule for the generator, calculate the EMF produced by the simple generator, identify the main component of the DC rotating machine, and draw the connection and equivalent circuit of the separately excited DC generator. The DC generator converts the mechanical energy to electrical energy. The action of the DC generator depends on the mutual electromagnetic induction. So this will be the generator operation. So this is the coil A and B. In the magnetic fields are and not to solve the magnetic flux are flowing. So this is the A and B coil. So A and B are rotate this way, and then in this case the current will induce. In this case here this side is the current flowing to here this is flowing going down. So the body induce like this. The next one. And this will be body like this, that the current direction. And this direction, then this is the current direction, and the body into like this. And the next one, they like this. So this will be the generator operation. Output of the generator airbars are alternating current. It must rectify it to convert to the direct current. So this is the alternating current. Direct current is a red one. So after rectification, output is a pass DC. So this pass DC provided by the commutator. So this is a commutator. The commutator rotated like this. So the output will be the DC. So that the generator is a voltage depending on the flux density P, Tesla, less as a meter and a velocity V. So E equal to BLV. So we have to calculate the EMF induced in the 200 millimeter length of the wire. If it is moved through the magnetic field with the flux density of 0.5 Tesla at the velocity of 12 millimeter per second. What do we know? So we know about the A is 200 millimeter, B equal to 0.5 Tesla, and the velocity V is 12 millimeter per second. What do we want to know? E equal to BLV. So the 0.5 multiplied 200 minus 10 power minus 3 minus 12, you got there 1/2 volt. The next problem, a single loop of the wire is moved through the magnetic field with the flux density of the 0.5 Tesla at the velocity of 12 millimeter per second. If the each side of the loop has a length of 200 millimeter within the field, calculate the EMF induced in the one side of the loop and the loop. So what do we know is, we know about the flux density B 0.5 Tesla, velocity V the 12 millimeter per second, and Y is 200 millimeter. What do we want to know? E equal to BLV. So then we calculate 0.5 multiplied 200 minus 10 power minus 3 into 12, you got a 1/2 volt. And what is the F for the loop? So in this case, so we calculate A12 is 400 millimeter, so E12 is 0.5 minus 400 multiplied 10 power minus 3 minus 12, you got the 2/4 volt. The next problem, a DC generator armature wound using the 6 series connected coils on the copper wire. Each coil has a 40 turns and each side of the coil is 250 millimeter long. If the armature rotated in the magnetic field of the 0.8 Tesla at a velocity of 10 meters per second. Determine the EF induced in the 1 half turn, 1 full turn, 1 coil, and the entire armature. What do we know? We know about the B is a 0.8 Tesla, A is a 200 millimeter, velocity V 10 meters per second. So we want to know the E equal to BRV. So the A is in Tesla we calculated. In this case, we calculate the 1 half turn. So the A1 is a 2.25 meter, 1 full turn. In this case, A2 is a 0.25 multiplied by 2, 5.5 meter. And then we had to use a 1 coil is a 3 to 0.25 multiplied by 2 multiplied by 40, 20 meter. The entire armature, and so 0.25 multiplied by 2 multiplied by 40 multiplied by 6, you got 120. So that in this case, coil to 6, and equal to 40 turn, A equal to 250 millimeter, B equal to 0.8 Tesla, velocity V 10 meter per second, E equal to BRV. So the A 1.25, in this case, E1 to 0.8 multiplied by 10 multiplied by 0.25, you got a 2 volt. A2 is a 2 multiplied by 250 multiplied by 0.5 meter. So E2 equal to 0.8 multiplied by 10 multiplied by 0.5, you got a 4 volt. A3 is a 40 multiplied by 0.5 multiplied is equal to 20 meter. E3 equal to 0.8 multiplied by 10 multiplied by 20, you got 160 volt. And then A4 is a 6 multiplied by 20, 120 meter. E4 equal to 0.8 multiplied by 10 multiplied by 120, you got a 960 volt. The general magnetic field can be provided by the permanent magnet for the small machine or the electromagnet for the large machine. Generators are classified according to their magnetic field excitation, or the straight excited or the cell excited. So this is a DC generator. 1 is free. 2 is free coil. 3 is free pole laminated. 4 is free coils are ball. 5 is armature. 1 is free. 2 is free coil. 3 is free pole laminated. 4 is free poles are ball. 5 is armature. Those are components of DC generator. This is a straightly excited generator diagram. So this is a straightly excited machine, armature, and then supply. Supply is armature separately. So this is a connection of the wire. And this is the free winding. We provide a free load step. So this straightly excited generator can be drawn by this way. You can see the DC supply, free load step, free winding, and is a EG is a generator voltage, I is armature resistance, A1, A2 is a main armature circuit. Advantage allows a separate control of the output voltage. The excitation is not affected by the change in the load. So straightly excited equivalent circuit is this circuit. It allows a separate control of the output voltage. The excitation is not affected by change in the load. So the generator voltage depends on the flux density B, Tesla, length of the conductor, L, and the velocity V, each equal to VLV, or the each equal to 5V by 1. So that 5V by 1 multiplied by Z by A. Z is a number of conductor, A is a number of armature parallel paths. This is a lead type winding. So armature parallel path is equivalent to the pole. And here is a wave type winding. So armature parallel path is equal to 2. So this is lead winding and wave winding. So that we calculate that each equal to BL by BLV. So each is a generator voltage, B is a magnetic flux density, A is a dash, V is a velocity. Each equal to 5B by 1 multiplied by Z by A multiplied by N by 60. In this case, 5 is a plus, B is a pole, Z is a conductors, number of conductors, A is a number of armature parallel paths, N is a speed RPM. So this can be calculated EG equation. Generator voltage depends on the flux pi, number of revolution M, and then number of poles B, so that we can change the number of revolution flux pi, but we cannot change the number of poles. We cannot change the number of armature conductor Z. We cannot change the number of armature plus A, and we cannot change the number of seconds. So this makes up the machine concept. K equal to PZ by 60A. B is a pole, Z is an armature conductor, A is a number of armature parallel paths. In this case, K is a machine constant. So E is equal to P by 60A multiplied by phi n. So E is equal to K phi n. We have to calculate. Determine the generated voltage of the slightly excited generator with the machine constant of the 15, the effective free flux of the 0.08 Weber, and the operating speed of the 360 RPM. What do we know is that K equal to 15, phi equal to 0.08 Weber, and equal to 360 RPM. What do we want to know? E equal to K phi n. So this we calculate the 15 multiply 0.08 multiplied 360, you got a 438 volt. The next problem. Determine the generated voltage of the slightly excited generator with a machine constant of 15, effective free flux of the 0.1 Weber, and the operating speed of the 360 RPM. What do we know is K equal to 15, phi equal to 0.1 Weber, and equal to 360 RPM. So in this case, we effective free flux 0.1 Weber. What do we want to know? E equal to K phi n. So then with 15 multiplied 0.1 multiplied 360, you got a 540 volt. The next problem. Determine the generated voltage of the slightly excited generator with a machine constant 15, effective free flux of the 0.08 Weber, and the operating speed of the 500 RPM. What do we know? K equal to 15, phi equal to 0.08 Weber, and equal to 500 RPM. So this is our 500 RPM. So what do we want to know? E equal to K phi n. So 15 multiplied 0.08 multiplied 500, you got the 300 volt. The next one, DC generator part 2. At the end of this session, the student should be able to describe and interpret the no-load characteristic of the DC generator, describe the effect of the armature reaction, describe and interpret the load characteristic of slightly excited DC generator, calculate the voltage and the current in slightly excited DC generator. So this is a slightly excited DC generator. So this is a P winding excitation DC supply. This is a P rheostat. Armature output is a A1, A2. This is a terminal voltage. So this is the open circuit and no load. So when open circuit characteristic, when there's a origination magnetic free current, and this is output terminal voltage. When the free current flow, output terminal voltage will be rising. So this one is a residual magnetism, and when the current increase, voltage will be increased. Then it will be saturated. The saturation happen. This is a speed 1 and speed 2. The saturation happen like this. We have to calculate the determine the generated and the terminal voltage of slightly excited DC generator with a machine constant of 15 and the effective free flux of the 0.08 Weber and the operating speed of 500 RPM. What do we know is we know about the this is a connection here DC supply free rheostat and here is output terminal voltage. So the K equal to 15, phi equal to 0.08 Weber and equal to 500 RPM. What do we want to know? EG equal to K phi n, so the VD equal to EG. So 15 multiplied by 0.08 multiplied by 500, you got a 600 volt. VD equal to EG equal to 600 volt. So this is the generator. So in this case, there are no current in the armature, no distortion of magnetic field. So this is the magnetic and neutral plane. Normally, it's at the neutral position. No current in armature, no distortion of the magnetic field. When there's an armature current flow, the magnetic field is distorted in the direction of rotation. So this is we call the armature reaction. So because of the armature reaction, it can happen as sparking at the commutator and reduce the terminal voltage. Armature reaction can be overcome by the moving the brush from the central position to neutral and neutral point, effective for the load when the don't change too much. So this is for this field. This is for this brush. So this brush position you have to change. Armature reaction causes sparking of the armature, reduce terminal voltage. Armature reaction can be overcome by the moving brushes installing the compensating winding. Winding in the field poles are connected in series with the armature winding, used to counteract the armature field and shift the neutral point back to its central position. It is a most effective and most expensive method. So this is the armature coils, and this is for this is one magnetic nuclear plate, and this is the geometric nuclear plate. So this is the armature compensating winding we put like this. In this case, we can utilize the wiring on the yokes are connected. We also have to do this interpole. So the armature reaction causes the sparking at the commutator, reduce the terminal voltage. Armature reaction can be overcome by the moving the brushes, installing the compensating wirings, and installing the interpoles. Wirings on the yoke connected in the series with the free poles used to counteract the armature field and shift the neutral point back to the central position. This is the most common method. So this is the main free pole here. This is small pole. Small poles are interpole we connected. So because of this interpole, we can reduce the armature reaction. So this is a connection of the main free pole and interpole like this. So the P winding can be connected like this. So this is a P1 interpole. So this is the spatially excited generator. This is the effect of the compensating wiring. So the open closed circuit characteristic is that this is a low current and the open output terminal voltage. When the low current draw, terminal voltage will pull down. So this is the open voltage is that this is zero current at this position. And this is a full voltage at the full of current saturation. We have to calculate that a spatially excited generator has a field resistance of 125 ohm. And its supply for is 125 volt DC supply. If the generator has an open circuit terminal voltage 500 volt and armature circuit resistance on 0.25 ohm and the armature current of 25 ampere, determine the peak current generator terminal voltage and load resistance. So what do we know? We know about this is for the DC supply and the period set and this is terminal voltage. So we can calculate. So what do we want to know is the peak current is flowing 125 volt, 125 ohm. The peak current flowing, so the terminal voltage is 500 volt here. So in this way, IF equal to VF by RF, we calculated 125 by 125 equal to 1 ampere. Generator terminal voltage EG minus by IAI. Then the 500 minus 35 to 0.25, you got the 491 by 25 volt. Load resistance R equal to VF by IA. So the 491 by 35, you got the 14 ohm. The next problem. A spatially excited generator has a field resistance of 200 ohm and its supply for is a 250 volt DC supply. The armature circuit resistance of the 0.2 ohm and the load has a resistance of 10 ohm. Given the generator operates with the P flux of the 0.1 weber, its speed of the 1000 RPM and has a machine constant of 5, determine the P current, generator terminal voltage, load current, generator terminal voltage when the delivering the load current, and the voltage drop across the armature circuit resistance. What do we know? So this is a spatially excited generator, is a free load step and a spatially excited generator. Field resistance of 200 ohm we put here, and the supply from the 250 volt DC supply, and the armature resistance is a 0.2 ohm. So we have to know it. Flux line is a 0.1 weber. Speed and is a 1000 RPM, K is a 5. What do we want to know? We want to know the generator terminal voltage. So that this is terminal voltage here. And generator terminal voltage when driven load current, voltage across the armature circuit resistance. Those have to calculate. So when we draw the equivalent circuit diagram, 250 or 200 ohm. This is why armature circuit is a 0.2 ohm and load is a 10 ohm. So we write the equation EG equal to VD plus IL into I. In this case, the IF we have to calculate. Free current is a 250 volt divided by 200 ohm. You got a 182 ampere. E is equal to K5N, so 5 multiplied by 0.1 minus 1000, you got a 500 volt. I equal 500 divided by 10 plus a 0.2, you got that 49.02 ampere. V equal to 49.02 multiplied 10, 490 by 2 volt. V equal to 49 multiplied by 0.2, you got a 9.8 volt. And V equal to 500 minus 490 by 2, you got a 9.8 volt. So this is the way that we can calculate. So that when the phi is a 0.098 weber, then IF is 250 by 200 to 1/25 equal to K5N, so that 5 multiplied by 0.098 multiplied by 1000, 490 volt. I equal to 490 divided by 8 plus 0.2, you got a 59/7 say ampere. V equal to P 9/76 multiplied 8 so 478.08 and E equal to V equal to 9/76 multiplied 0.2 equal to 11.95. Therefore, the V equal to 490 minus 478.08 11.924. Then you have to do the exercise. So those are the G's 101. And then you also have to do the G108. We go to the side. So electrical trade. Go to electrical trade 2022. So that equal. So this is for the electrical trades that electrical trade 2022.htm. Then you go down and then you find out the G108. So G108, click this one. Then read the workbook. So workbooks are exercise. And read the workbook and do the exercise. And here is the answers are provided. So this is the workbook exercise answer. Also, that you also need to do this video, view the video like this. The next one is you also have to study the G105. This is a capstone compliant functional testing. So in this case, this capstone equation. Capstone lesson. Capstone lesson. This is for the capstone lesson. Capstone lesson, you can read here. This is a read through the capstone lesson. The verification and safety testing. Those are all the verification and the safety testing regarding the electrical capstone. So you also have to read through those notes. So this is what the G105 you have to do. Regarding the advanced diploma electrical engineering, you have to see this side. Then putting down. Finally, you got the electrical diploma 2022. So click electrical diploma 2022. Then you go down and see the YouTube video lesson. YouTube video lesson for electrical engineering lesson. Then you click the lesson. You have to do the H11, H13, H25, H26, and H045. So go down to our electronic units. Go down here and then you see the H011. Okay, H011 is a basic analog and digital electronics. So that is a DC power supply. So if you don't highlight computer.com/video lesson.pdf, so that you have to study the base 374 to 377 and you view the video. And H013 is an amplifier. So highlight computer.com/video lesson.pdf, so that page 378 to 386. Those are the written note and you view the video. And also the power electronics, H025 single phase operation, so the H026 is multiple phase. So in this case, you have to study highlight computer.com/video lesson.pdf, so that study the page 387 to 403 and you have to view the whole video. And also the H026 electromagnetic control. So the highlightcomputer.com/video lesson.pdf. You study the page 404 to 415 and also view the video. Another thing is 8045. Analogs are electronics. Analog electronics, so they are highlightcomputer.com/video lesson.pdf. So you have to study a page 416 to 428 and then you view all the video. So this is the way you have to study.